After a long back of say 1 year approximately, I have again come to do the video lectures on the remaining part of chemical kinetics. Up to the lecture 4, I have already done this video. Now today I like to talk with you very casually the second order reaction, kinetics of second order reactions, and this is part 1. This is part 1. Means it is the preliminary discussion of the second order reactions meant for 10+2 examinations and also for the IIT-JEE and the NEET, etc. And next, in my next class, I will discuss the part 2, which is a little bit advanced, and it will be meant for the honor standard and very useful for NET, GATE and the IIT-JEE. So now I start the reaction. Say second order reaction means the rate of this reaction depends on the two concentration terms, and two reactants will be there. Say it may be one A plus A and giving you the product P. Means both the reactants are identical and they are combining, reacting, and to give you the product P. And the rate of this reaction are equal to K2 and concentration of A square. 2 is given, for it is the second order reactions, means two concentration terms are there in the rate equation, and this rate may be represented as minus dCA by dt equal to K2 and concentration of A square. K2 is the rate constant of the reaction. This constant for a reaction at a given temperature, and it depends on temperature and also the nature of the catalyst if used in this reaction. And this dA concentration by dt, it is the decrease in concentration of A with respect to time. Means as T is advancing, dt is positive and A is decreasing. As the concentration of A is reacting, the reactant A is reacting, so its concentration is decreasing. So this one numerator negative, denominator positive, then whole term is negative, and here it is negative. So this one is positive. Rate is always positive term. Rate is always positive term. This one negative, this one positive, negative by positive, negative, and here it is negative. Both the two multiplied give you the positive term. Rate is positive. Another type may be there A plus B. Two different substances. Two different substances are combining to give you the product P. In this reaction, we can also write rate dA by dt. The rate is referring with respect to the reactant A, and this is equal to K2 and concentration of A and concentration of B. Both the concentrations are affecting the rate of this reaction, and K2 is again the rate constant, and this one the rate positive. This is the rate equation. And in this case, suppose we may take for our own experimental convenience convenience. So convenience, we can write this concentration of A naught equal to concentration of B naught, means the initial concentration of A and B are kept equal. So its mathematical format is easy, and not only that, the experimental method to determine the rate constant or any sort of kinetic study becomes more easier. So in this case, then since initial concentrations are the same of the two different reactants, and these are combining 1:1 mole, means stoichiometric ratio 1:1. So at any time after this reaction, at any time after the start of this reaction, in any time both concentration of A equal to concentration of B. These two concentrations will remain the same always at any time during this reaction. So in this case we can write minus dA by dt equal to K2 and concentration of A and square. So this rate equation and this rate equation is the same, and mathematical format, mathematical treatment will also be the same. If they are not, if the concentration of second type, if concentration of A naught not equal to concentration of B, means two different reactants having the different concentrations. Here third bracket indicates the moles per liter concentration. So not equal, then this will be the rate equations, and in this case the treatment will be different, and mathematical deductions will also be mathematical deductions, and also the experimental process, both are little bit difficult. This is why we always keep both the reactants having the same concentration, though they are different reactants, but initial concentration have been kept equal. So there might also be reactions, so say A plus B plus C, and giving you the product. So in this case the rate minus dA by dt in terms of A equal to say K2 concentration of A to the power half, concentration of B to the power half, and concentration of C. In this case half plus 1. So it is also the overall order is 2, and treatment will be the same. It is rather little bit more complicated. So let us start with this rate equation, this one, and today our discussion will be limited to this rate equation only. So the integrated form of this rate equation can be obtained by dA concentration, and this one coming here, concentration of A square equal to K2 into dt, means the variables are being separated. Right hand side is time variable and left hand side concentration variable. So variables are being separated by this mathematical process. Now we can integrate, and you know this integration is very easy, and you have already learned in class 2 courses. And suppose say dx by x square integration equal to minus 1 by x. So in this case also will be say limit t equal to, when t equal to 0, the concentration is A naught, initial concentration. When t is t, at that time t, the concentration is A. So if we do the integration and put this limit, then it will be minus 1 by A naught and here concentration of A equal to K2 and here T and 0 to T. So if we do the limit, then it will be 1 by concentration of A minus 1 by concentration of A naught and equal to K2 T. Or if we shift this term to right hand side, then 1 by A equal to K2 into T and plus 1 by initial concentration of A. So this is the one form, this is one form, and we shall write here the 1 by A equal to K2T plus 1 by concentration of A naught. The second form can also be obtained here by taking the subtraction say concentration of A and concentration of B, and here concentration of A naught minus concentration of A equal to K2T. So this one is the alternative form, concentration of A naught minus concentration of A divided by concentration of A naught equal to K2T. So this is one equation, this is two equations. These two equations are used. These two equations are very important. They are used to kinetic study of this reaction. Say suppose to determine the rate constant K2. If we know, this is very essential experimental data, experimental kinetic data, at different time intervals, the concentration of this reactant A remaining unreacted is determined at different time intervals, and this is very important, either by chemical method or by physical method which you think suitable to determine the concentration of A at different time intervals. Say if you whenever you determine the data, collect data, say suppose here is the table, here concentration of A and here time t, and here concentration of A. Say T, when T equal to 0, concentration of A naught, when T equal to T1, concentration of A1, when T equal to 2 and concentration of A2, and T equal to 3 and concentration of A3, and different data you can receive, collect from your experimental study, experimental determination of this concentration of A at a different time intervals, either by physical method or by chemical method which you think suitable for your own experiment. So these data, by the use of this equation, you can easily calculate the rate constant of this reaction. Say suppose equation 1, you are using this equation 1, and so in this case you just do the plot, here the time here 0 and concentration of A, 1 by concentration of A, 1 by concentration of A equal versus T. So it will be the equation y equal to mx plus c. So it will be a straight line having an intercept. So this will be the graph. This intercept will be 1 by A naught, and slope means tan theta, and this is give you the value of This will give you the value of K2 rate percent of this reaction. By easily using this equation 1, by using the equation 1 and getting this data, kinetic data, you can determine this K2. Once the K2 is known, and if you know the initial concentration of this reactant, then at any time you can calculate the value of concentration A remaining unreacted. Not only that, if you know the K2, then at any time the suppose concentration of A is A2, say concentration of A is suppose this one and T2 is this one. So you can get this rate of this reaction. Rate of this reaction at any time you can calculate by using this rate equation, and this is the beauty of this rate equation. If you know the K2, then at any concentration of this reactant you can find out the rate at that time. So another plot we can also design for by using this equation 2. Equation 2, say this one. Here the y-axis, here t is the x-axis, here it is 0, and y-axis is a naught minus a divided by a naught. If you do the plot, then this plot will be equal to 1 y equal to mx. So simply a straight line passing through the origin. So this one suppose theta. So slope equal to tan theta, and this one the value of K2. By the use of this equation 2, utilizing this kinetic data, you can also easily get this value of K2. Now I like to explain some salient features or characteristic features of this second order reactions if the reaction is A plus A, giving you the product P. First salient feature, say 1, say half-life period. Half-life period of second order reaction, say T half. So T half you can easily find out from this equation 1, either from equation 1 or from equation 2, which you think best. And from equation 1, say when T equal to T half means reactant is cut to half, reactant is half decomposed, that time T half, and at that time concentration of A equal to the initial concentration by 2. Initial concentration becomes a half of the initial concentration have been decomposed. So putting here, it will be 2 by concentration of A naught equal to K2 T half and plus 1 by A naught. Simple mathematics, and you can show this T half equal to 1 by K2 concentration of A naught. So this is the third equation. You can write T half equal to 1 by K2 concentration of A naught. So in this case, it is seen that the half-life period of the second order reaction depends on the initial concentration, or rather very accurately you can say half-life period is proportional to 1 by initial concentration. 1 by initial concentration. It is very surprising. If you double the initial concentration, of the second order reaction, then the half-life period becomes half. Means half-life period cut to half whenever the concentration, initial concentration of this A, you do it doubled. So this is very surprising. You can say for means the greater the amount of this reactant, the time required for its half decomposition is less. Our thinking is that if we take this larger amount, then its half decomposition will take the larger time, greater time. But in this case, it is different. This difference is coming due to whenever we are considering the second, rate is increased. If you take this amount of or concentration of this reactant is greater, then rate becomes a high. So rate becomes high means its decomposition becomes less. You see, if you double the concentration, then rate becomes 4 times. If you double this rate concentration of this A, the rate becomes 4 times greater. So rate becomes higher means a time required for half decomposition is getting less. So you can think for the first order reaction, for the zero order reaction, this is for first order reaction, it is only the 0.693 divided by K1 means half-life period is constant. Half-life period is constant. Only in case of zero order reactions, the half-life period is directly proportional to the initial concentration of this reactant. Greater the amount of this reactant you have taken, greater the time required for its half decomposition. In first order reaction, whatever may be the amount of the reaction to cut for half decomposition, the half-life period is same. But in case of second order reaction, if you take a greater amount of this initial concentration of the reactant, then its half-life period becomes less. It is very surprising. This is due to the fact that the rate is depending on the concentration of the reactant in different way. In zero order, rate is independent of the concentration. In first order, rate is directly proportional to the concentration of the reactant. In second order, the rate is directly proportional to the square of this concentration of the reactant. This is why the half-life period, features of half-life period is having the different meaning, different dependency. And to unit of K2. Unit of K2. If you the unit of K2 equal to say K2, it is concentration square means concentration inverse and time inverse. If you take this concentration in moles per liter, then it will be mole liter, mole inverse liter and second inverse. If you take this time in second, if you take the concentration mole per liter. But if you like to change this unit, say instead of mole inverse you can take this molecule inverse, instead of liter you can take it cc, then magnitude of this rate constant is also different. One example I can set up, say hydrogen peroxide, say twice HI decomposing as H2 plus I2, and at 556 Kelvin this K2 equal to 3.5 into 10 to the power minus 7 mole inverse liter second. If you like to express in molecule inverse Cc second inverse, then this magnitude will be different. So K2 equal to 3.5 into 10 to the power minus 7. Instead of mole we can write molecule 6.025 into 10 to the power 23 molecule inverse. Instead of liter, we can write 10 to the power 3 cc and second inverse. If we do this one, then it will be 3.5 into 10 to the power 7 and divided by this one coming to the denominator 6.023 into 10 to the power 23 and into 10 to the power 3, and this will be the magnitude, and here it will be unit will be molecule inverse Cc and second inverse. So if you do these calculations, it will be 5.8, and this will give you the 5.8 into 10 to the power minus 28 molecule inverse Cc second inverse. So this will be the whenever you are changing this unit of this K2 and the magnitude of this K2 becomes different. So the rate constant depends on the choice of unit of this rate constant you have taken. And third criteria, the incompleteness of the reaction. Incompleteness of this reaction. From this you can see, from equation 1 or equation 2, you can see when the reaction is complete, this concentration of A equal to 0. It means there is no reactant being left for this reaction. Reaction is complete. So this A is 0, means 1 by 0 equal to K2 into T plus 1 by A naught. This 1 by something by 0 equal to infinity, equal to K2T and plus 1 by A naught. So this is constant, this is also constant. So T, this equation can only be possible when T is infinity. So whenever the reaction is complete, T tends to infinity. Means at an infinite time the reaction will be over. Means in a finite time the reaction will never be complete. It remains incomplete. So this fourth criteria, fraction of A decomposing in time t. Fraction of A decomposing, you can see that this one is the fraction. Now this one, from this one we can get it A naught minus concentration of A divided by concentration of A naught equal to concentration of A and K2 and T. This one is the fraction of decomposing. Numerator is the amount of a decomposing divided by the initial concentration. So this will be the fraction of this reactant A decomposing in time t. A, the concentration of the reactant at this time t. A variable, T variable. As T is increasing, this one is decreasing. So we shall have to change the right hand side of this term in one variable. So from this one you can get this term from this one. Say 1 by A equal to this one. 1 by concentration of A equal to this concentration of A naught, and here 1 plus one plus concentration of A naught and K2 T. So A equal to concentration of A equal to concentration of A naught divided by 1 plus concentration of A naught and K2 T. This is the concentration of A at the time t. This is the concentration of A at the time t. So this one could be replaced by right hand side. So whenever this one is replaced in right hand side, we have this is equal to concentration of A naught K2T, concentration of A naught K2T divided by 1 plus concentration of A naught and K2 T. Right hand side except T all are constant. So at any time T this will be the fraction. If we arrange this one in a similar in our casual way, then we can write this one 1 minus, this one will give you the one by 1 minus 1 plus concentration of A naught K2 T. So this is the fraction of the decomposition. This one is the fraction of decomposition. I hope you can easily manage the mathematical portion from this one coming. So this is the fraction which has been decomposed at this time t. This one, the fraction remaining undecomposed, and this fraction undecomposed. This one is the fraction remaining undecomposed, and this one total is the fraction of A decomposing at this time t. So from this relation is very good, and from this relation you can find out the different values. 1 minus 1 by 1 plus concentration of A naught and K2 T. From this you can easily get this half-life period. This value automatically come up from this one. Whenever the reaction half-life at this, when T equal to T half, then this fraction concentration of A naught minus concentration of A divided by concentration of A naught, this fraction is equal to half. So half equal to 1 minus 1 by 1 plus A naught and K2 and T half. If you do this problem, if you solve this one mathematical form, then you will get this T half equal to like this one. So not only that, you can calculate the calculate the time required for 75% decompose. 75% when T equal to T 3/4 means 3/4 of this reactant have been decomposed. So in this case this one will be equal to 1/4. Remaining this one is the decomposing 3/4. This one is the fraction decomposing 75% decomposed. So if you put here the 3/4 equal to 1 minus 1/1 plus A naught into K2 into 3/4. Then you can see it by simplification. You can do it. This one coming here, this one going there. Then 1/1 plus A naught into K2 into T 3/4 equal to 1/4. So 4. So 1 plus A naught K2 T 3/4 equal to 4. Or you can say 4 minus 1, 3. So T 3/4 means T 75% decomposition equal to 3/3 K2 and concentration of A naught. So this is the time required for 75% decomposition. 75% decomposition. So if you take this ratio T half by T 3/4 equal to, it will be 1/3 constant. And this whenever we do the nth order reactions, we can find that this one could be written as 1/2 to the power n minus 1 plus 1 for nth order reaction. Nth order reaction. If you take this as first order reaction, then it is half. For the second order reaction, it is 1/3. It is 1/3. And say for third order reaction, n will be 3. So in that case, 3 minus 1, 2, 4, 4 plus 1, 5, 1/5, and so on. So from this relation, this ratio will give you the value of n. If you can calculate this half-life period and 3/4 period of decomposition by experimental method, graphical method, then you can find out the value of n. N means order of this reaction. This is one of the very important method to determine the order of this reaction. So this is all about the preliminary discussion of this second order reaction, and in my next class I shall try to go for this part 2, which is little bit more advanced and required for the honors students and NET, GATE and other competitive, national competitive examinations. So thank you all for watching my video.